Transfer of an electron. If an atom A has an ionization energy of 5 electron volts and another atom B has an electron affinity of 4 electron volts and they are 5 angstroms apart, calculate the energy required to transfer an electron from A to B. Okay, so our task is to transfer. So now to transfer an electron from A to B, we have to consider the steps in doing this. So the ionization energy, that means we need 5 electron volts to rip off an electron from atom A. So this is our ionization energy. At this point, we're assuming that atoms A and B are at infinite distance. We just need to supply this energy to atom A, isolated atom A, in order to extract an electron from it. And now, when the atom B accepts an electron, 4 electron volts will be released. When B gains an electron, that is the electron affinity of atom B. So these two atoms are at infinite distance. One has released the electron, the other one has gained the electron. Now we're going to put them at a distance 5 angstroms apart. So in doing so, there will be some energy released because we have a positive ion and negatively charged ion. They will have an attractive potential. So the electrostatic potential energy released will be the energy that will be released when bringing them from infinite separation to 5 angstrom distance. The electrostatic potential energy in electron volts is minus the Coulomb constant K electron charge divided by R, the distance between the atoms. So you will remember that this potential energy is kq square over r, but because these are the charge is 1 electron, so we divide kq square over r with 1 electron charge to obtain the answer in electron volts, so instead of joules. This is basically minus, if I use the Coulomb constant, 9 times 10 to 9 newtons meter square per coulomb square, electron charge 1.6 10 to minus 19 coulombs, divided by the separation 5 times 10 to minus 10 meters, that's 5 angstroms. So we're using for Coulomb constant 9 times 10 to 9 newtons meter square per coulomb square. The answer comes out as minus 2.88 electron volts. So total energy required in order to perform this charge transfer, total energy required is the ionization energy plus the electron affinity plus the electrostatic energy that we need. The ionization energy is supplied to atom A. So let me take this upstairs here. This total energy required will be 5 electron volts to rip off the electron, 4 electron volts released when gaining an electron, and also 2.88 electron volts is released when bringing these atoms together to a 5 angstrom distance from infinity. So that's minus 4 minus 2.88. So that means minus 1.88 electron volts. So when the task is completed, we will have 1.88 electron volts released in this process. Okay, so we are trying to transfer an electron from atom A to atom B. Atom A has ionization energy 5 electron volts, B has electron affinity 4 electron volts, and they are at 5 angstrom distance. First, we supply 5 electron volts ionization energy to atom A to ionize it. Then we release 4 electron volts when B gains the electron. Then we bring them together from infinite separation to 5 angstrom distance because we have an attractive potential here. This amount of energy will be released in the process, so the total energy required will be ionization energy plus electron affinity, which is basically going to give us minus 4 eV contribution, and plus electrostatic energy, that will be minus 2.88 electron volts, because 2.88 electron volts will be released when these atoms are brought from infinite separation to 5 angstroms. So in total, we find 1.88 electron volts of energy will be released in the process of transferring the electron.